A final significant topic, and bearing in mind that I don't want to dwell on this, but it's a very important conceptual topic as well as has some practical texture to it. So if we go to versions of these things for discussion, I'd like to draw your attention now to the calibration, slide set of slides. Okay, and we're going to go through this in sort of a wind way. You'll find me talking about it in great length online, and I don't want to try to duplicate that at all. Okay. Good. So, calibration. So model parameter estimates come from a variety of sources, and these are frequent data sources that we make use of. So in some cases, you're lucky and you can find meta-analyses that estimate the value of parameters. For example, some work in TB, there's quite excellent meta-analyses done by Kolditz and others to estimate the efficacy of BCG vaccination, etc. And this can be, an excellent source of data. In other cases, we're reduced to what's sometimes called expert judgment, or sort of best guesses for parameters. But there's a wide variety of cases where we make use of other data. Some of it from some sorts of surveillance, controlled trials. So in the States, it might be survey instruments like NHANES or NHIS or BRFSS for the behavioral risk factor data. In Canada, NGSS, the National Population Health Survey, the Canadian Communities Health Survey, CCHS, and others. There are cases where there's controlled trials that also sometimes observe some data, but it has to be careful of the difference between sort of effectiveness and efficacy. Data from outbreaks that you might be able to make use of, etc. Often, however, there is a situation that results where we don't have reliable information on some parameters, but we do have other data. So we have data quite frequently that relates to the emergent behavior of the system as a whole, and not to the behavior of any one component of the system. So it doesn't, by itself, allow us to directly estimate a parameter, but instead, it speaks to what sort of emergent behavior you note from the system as a whole. And actually, Alexander put his finger on this a couple days ago. Although he may be new to the material, he advanced a quite sophisticated concept that sometimes you have data about how the system behaves, and that's a complex result of a lot of different factors. It may be for an infectious disease like TB in the third world, or a very severe illness like HIV. It's going to be shaped by a lot of things: mortality rates and incidence and reporting, all those sort of things. And you're not going to be able to take that data and typically put in information directly for one particular parameter. But it says something about how the system behaves that's still useful. It still gives us constraints as to what our interpretation could be for parameters. Sometimes the data doesn't have the specific breakdown to address one parameter, but it allows us to sort of constrain or inform what plausible selections are of possible parameter values. There's two big ways of dealing with this. There are cases where you can manually so-called back out parameter estimates from this, and I have some examples of the slides I won't be able to discuss. But the other thing I did want to discuss in more detail is automated calibration. And the idea here is that we're seeking for a model that closely matches a variety of data sources. This is actually a system dynamics model that came out of our work here. So NSAID renal disease for diabetic patients, as well as type 2 diabetes, based on 25 years of administrative data in the province. And here we're seeking our model, it's shown in red and gray, to match up the data from population-wide repositories or administrative data on diagnosis, for example, on diabetes, population data, data on deaths, from death records, etc., in such a way that it simultaneously matches all of these things. We want to keep the model honest, keep it grounded by trying to match it to a wide variety of data. And even if this data is not sufficient to allow us to estimate one particular parameter, we may be able to, it may be telling us a lot about what possible parameter values are. So you can view at a very high level the calibration process is sort of triangulated in a computational way from diverse data sources. So in its classic form, it involves tuning values of less well-known parameters to best match the observed data. Okay? So we're adjusting parameter values to try to gain some understanding of their underlying values by matching up the model against historic data and trying to maximize the quality of that match to arrive at estimates of these parameters. Now, I work, as some of you know, I work in several methodologies related to this. Some of my most recent work that I'm most excited about is an application of Bayesian Markov chain Monte Carlo techniques together with simulation models that give you not just point estimates of parameters, but distributions, posterior distributions over parameters of what values those parameters might take on. And I won't be talking about that here, but be aware that it is a point of sort of cutting-edge work within simulation modeling that could also work together with discrete event model, with agent-based model if desired. In fact, with all of the techniques here. But here we're talking, I'm going to be introducing you to this idea of trying to estimate point predictions for parameters by best matching underlying data sources. So this observed data to which we're matching may involve many, many pieces of disparate data, some about deaths, some about incidents, some about prevalence estimates, some about screening results, all these things. We're trying to get the model to match all of it, to stay true to all of it, to be consistent with all of it. And to do that, we're adjusting values of parameters that we don't know that well. And one of the best things about this process is it keeps us honest as modelers. Because sometimes, quite frequently, what we find is the existing model structure doesn't cut it. You might think you could find all sorts of matches. And occasionally that's true, but if you have enough data, or if you have a model structure that's far enough off base, often you find that you either can't do it or there's actually a fairly narrow range of interpretations. If you have a model whose structure is off, it's missing some important states, for example, you may bend yourself backwards. You're not going to be able to find a good match for the data. It just doesn't jibe with what's possible with that model. So calibration can be seen at a high level as trying to help us find a specific sort of dynamic hypotheses, not just about the mechanisms, but about the values that explains the observed data. This isn't necessarily the truth, but it's probably a reasonably good guess. At least it's a consistent guess, a guess that's not obviously on the face of it sort of off base. And it helps us leverage often the large amount of diffuse information we have at our disposal. Information that doesn't inform one specific parameter, but instead constrains our interpretation of model parameters. And it helps us, to some degree, falsify models. Helps us, as I say, keep us honest. I should just note here, because it's so important, I wish I could feature a whole lecture on it, but there just isn't time. The issue, the notion of cross-validation, which is very important, where you can reserve part of the data that you have, put it aside, build the model without that data, and then see if you can reproduce. So when you have that model, you see if you can reproduce the data that you had put aside, that you hadn't used in the model building process, that you in a way had kept in escrow. See if it has predictive validity in that sense. But let's talk a bit about how calibration works. So calibration uses a global optimization algorithm to adjust unknown parameters so that it tries to match an arbitrarily large set of underlying data. The data, which ideally is in the form of time series, informs what we call the objective function of the calibration. the measure of goodness or badness of fit that we are trying to optimize. And typically an optimization algorithm will run the model many, many times, sometimes thousands or more of times, to find the best match. So what do we have to specify for calibration? Well, we have to specify what to match. What are we trying to match up? What empirical data with what outputs from the model? And how are we going to judge goodness of fit, or so-called payoff or penalty function? So how do we judge, for example, how bad a given match is? And if you have an error function, if it measures how bad a match is, we call it error function, penalty function, or energy function. That's how far off we are. And we'll see this in AnyLogic in a few minutes. And then we also have to specify what parameters do we want to vary, over what ranges do we want to vary them, for example, within parameter space. We may specify constraints on those parameter values and constraints on what legitimate model output would be to be counted as legitimate calibration, and characteristics of the desired tuning algorithm. So the idea here is we're trying to explore some parameter space. Imagine if we have 3 parameters, which are denoted with Greek letters to spare ourselves running off names, and we're trying to find plausible values of mu. Maybe mu is mean time, mean incubation period for this disease. Maybe beta here is something to do with a contact rate, and maybe tau here is something to do with waning immunity. We're trying to explore plausible values, sets, combination of values for each of these 3 parameters that will best explain the set of data that we have at our disposal. Okay. The idea is for each point in the space, we're going to need to figure out how good or bad the match is. Let's say how bad the match is. We're trying to minimize the badness of the match by, in other words, get it as close as possible, minimize the discrepancy of the model relative to the empirical data. So here, typically for each historic datum, each data point that we have, we're going to calculate how far the model off is for it, and then we'll apply some function to those. Maybe it's a sum of squares, and I give some features here for what a nice metric is. So it's dimensionless and weighted, and analytic and concave. That's probably not of great interest to people, but there's some theoretic backing for this. So sort of a naive idea here would be, if we were to start in this space, we imagine that we start in the space and we have a certain badness of fit. Imagine if it moves around in the space, trying to find a better and better fit, as if it's descending on a hill. So we start with a big discrepancy. Imagine the distance from the floor to my finger, indicating a level of badness of fit. And we're moving around in this space, and maybe it's getting better over time, and eventually we get down as far as we can, and just can't get better than that. A naive algorithm would stop there. More sophisticated algorithms would explore. They'd allow a little bit of going uphill in the hopes that you might then be able to go downhill in a big way, in an aggressive way. So maybe you have to get just up above a lip of a little sort of a little local minimum, and then you can go down a great deal. Imagine a lake on the hillside of a mountain. You have to go just up the end of the lake, and then you can descend even further. So they'll allow for a little bit of latitude, and then eventually get down to a level you can't go down any further. This is the sort of thing which is going on here. The key point is it's adjusting the parameters and judging each one. Okay. If you go into SAR agent-based calibration, or the version we've been working with, you'll notice that there's a calibration experiment here. And this is really what I want to point you to. Because the good news here, folks, is that that in contrast to other platforms, AnyLogic has, to many other platforms, AnyLogic actually has a quite sophisticated calibration mechanism built in, including for what are called stochastic calibrations. So calibration including stochastics, which are front and center when it comes to agent-based models. So if we go to this calibration experiment, what we'll see is a whole host of information related to this calibration. So if you go to the General tab, you should see something like this. First of all, oh man, I should have said that. Folks, every experiment you run, whatever this experiment type is here, every one we've looked at, be aware that you can either tell it to use, by default, different random seeds. Each time you run it, it gives different results. Or you could tell it, if you want it to be reproducible, you can use the same fixed seed every time. In other words, you can have it sort of replay the same Groundhog Day scenario each time. It's the same thing again and again each time you run that. Just being aware that you can choose between those is useful. Yes?
When you say stochastic calibration, you mean calibration of the model,
which exhibits stochastics. Yeah, exactly. Great question, because it's a video experiment, as you know. And here we have a model that, for a given combination of parameter values, say beta equals 0.1, mu equals 0.7, and tau equals 13. If I run the model with that assumption, each time I run it, will in general give a different result. And I need to be able to calibrate in light of that. Which, for many, many years, for example, in VenSim was very, very painful. They improved that since. AnyLogic has a comparatively sophisticated optimization machinery built on top of what's called OptQuest, which is a sort of popular endgame for optimization. So that exists outside of AnyLogic. So here's the optimization experiment, and what you'll find here is that you specify a set of things. So one set of things that you specify is, for example, the number of runs you do in this quest for finding the best set of values. You vary parameters within some ranges according to some steps if desired. And you'll see that we also end up specifying some way of judging how good the fit is. In this case, it's with a built-in method called difference, which compares two data sets, one involving historic data and one from the model, compares them and judges how good the fit is. Okay, so this is set in the context of the calibration. We sort of run the model, we get some data out of it for that particular run, and then we judge how good it is, how good a fit it is to the historic data. Ken. Right.
I think what the challenge that I kind of encountered in working on my project is I have an existing data set with what time series that's real-out.
Right.
So it's presented as a distribution curve, and that's really the kind of the end result of that.
Exactly.
So reporting gap.
Precisely.
So we don't really know what was the underlying dynamics, why that shape of the output was like this.
Yes.
That's right. So the purpose of this is trying to predict retrospectively the potential combination of factors or parameters that would explain the shape of that curve. The complexity was that it still cut out with the same information.
Right. Right.
So the challenge here that sometimes the parameters, let's say, so the how many susceptible, how many we use, what is the rate, contact rate, how we determine what is the probability of getting infection, can change, or actually not will change.
Will.
It changes over time. The reason why our rates occur is that the rate is dynamic. It's not a static event. In the beginning of the outbreaks, you have some certain amount of susceptible individuals and a great amount of immune individuals. And so it is a kind of a critical trend sometimes. So when one infectious case is introduced in an environment that's surrounded by a large number of susceptibles, that's what starts happening, or sets the outbreak.
That's right.
And then therefore the contact rate could be very small
Mm.
at the beginning of the outbreak, and your probability of getting infections at the beginning of the outbreak is quite small.
Right.
When it's progressing,
Right.
that can change. Speaking of contact, when you're trying to find the true value
Yeah.
or whatever, so there's an additional dimension that this how it happens.
Yep.
So I don't know whether the model can predict that or not, but it change over time. So any given parameter
so that's a great question. And the broad answer is yes, that you could have underlying factors like that changing. But maybe what that would mean is that beta, some quantification of the contact rate combined with likelihood of transmission for this coordinate contact, maybe that would in fact need to be unpacked into two more parameters, instead, to be replaced by two parameters. One having to do with sort of people's level of risk perception, or one having to do with their their propensity to change their contact rates under observations of an outbreak, or under something like an intervention, advisories or warnings that are issued. So you could actually accomplish that, and this mechanism is designed to certainly be general enough to accommodate that. That sort of logic would need to be in the model itself. But this sort of mechanism can readily be used, given a model like that, to try to identify parameter values that we don't know so well. And often it's things like, how does risk perception or reports of illness end up affecting people's behaviors? That's almost a classic case of a parameter it's hard to estimate, sort of from classic surveys or from administrative data. You're just not going to find that so readily. What you will get is data about what in fact happened in terms of people's infection rates and so on, and maybe you'll get information from schools on absentee rates or something like that. You may be able to go back from that, and calibration would be key to this process to estimate sort of what those underlying parameters plausibly are that you're not going to be able to observe directly. So I'd be glad to talk about that further. But it's a great question. So the point here is, folks, for each point in the space, we're going to have this model run. We're going to produce some data and try to compare it to the historic data. And AnyLogic provides some functions to do this. You'll note that, okay, I'm trying to figure out how much detail to go into here, but you can also define a custom difference function if you want to define your own instead of building in your own. Generally speaking, you will have to tell the calibration machinery about the empirical data that you have. So you may want to put into what's called a table function in AnyLogic. Ladies and gentlemen who are interested in working with situations where you have large amounts of data, table functions are very, very useful in AnyLogic. We're trying to get them generalized to handle multivariate data additionally well, and multivariate distributions to be created with them. But the basic issue is here. You can have a function that maps from some value to another. So this might be time, for example, and it specifies for each point in time what was the observed data. Maybe it's the days, some reference point for the beginning of an outbreak, or what have you. So here we can input data into these table functions. Once you have it in a table function, there's all sorts of things you could do for it. You could create a custom distribution based on them, or here, what we can do is load it into a data set, and then we can use it to compare with the data from the underlying model during the calibration process. And you could see this is actually where that table function data goes into a data set. So it populates a data set from that. Now, and then we're going to run through and systematically sample this. Now, the issue is more textured here than it is with a classic compartmental model. Calibration is done with compartmental models on a routine basis. The issue here is that with ADMs, just like with discrete event models, you typically have stochastics, and sometimes very significant stochastics. And most notably when you're dealing with something like infectious diseases or risk factors for certain types of chronic diseases, where you have processes of contagion, whether it's spread of ideas or innovation or spread of pathogen, you have an unstable system, and stochastics can yield big differences in results sometimes. So here we have to have a calibration machinery that tolerates stochastics. What do I mean by that? What I mean is we have to recognize that when we're exploring that cube, that blue cube, that any given point within the cube may yield different results each time we run it. So if we run the model with this value of mu, this value of power, and this value, maybe it's back into this gelatinous cube of beta, if we run the model with that combination, we may get different results each time. Each time it's going to be slightly different. Remember, we saw that earlier. We ran the model again and again and again with the same parameter values, and it gave some differences. So here, we want to find the best match to our historic data, bearing in mind that sometimes we may be unlucky, sometimes we may be lucky, sometimes a really good batch may be just a fluke of the random number generator, and we want to run it quite a few times in short to be robust. So within AnyLogic, fortunately, we have the opportunity to do that. So there's a notion in AnyLogic's documentation. Its terminology on this, unfortunately, is just is not consistent in terms of the naming. There's inconsistent names used sometimes, but the basic idea is we have this thing called a replication. That's the most common name for it, which is basically a realization. It's one of the model with a specific random number seed and a specific set of parameters. So it's a single run of that model. Main is run one time. Then there's a simulation, which is a collection of replications for a particular set of parameter values. And then there can be experiment, which is varying parameter values over it. Okay, so what we can do is we can set up many realizations for a given model. So you could set up these replications, use replications in the replications tab of the experiment. And here we could set, for example, to use 10 replications, 10 runs of this model for each specific vector parameter values. Each specific value, beta equals 0.7, mu equals 0.3, and tau equals 13. We could use, we run this model 10 times. Just like that, and hopefully faster than that. And it'll run, and it will consider all the variability in those runs, but most notably, it'll take the mean of how well they match the historic data, instead of just privileging one of those realizations. It'll run it in short 10 times, okay? And we can actually specify stopping conditions to allow it to run more times so that we have a certain level of statistical confidence. I don't have time to go into this. In my YouTube videos, I explain in great detail how this is all accomplished within the model. There's no magic there. And one of the examples in the exercises on calibration will help you understand this better. My students tell me, some of my students will come to me and said, really, it's after doing that they've really understood what's going on behind the scenes. But my YouTube videos on this are quite detailed as well. Bear in mind that in the calibration machinery, you can further specify constraints on parameter values. So maybe you want to allow beta and tau and mu to vary within some ranges, but they all have to sum to less than 1 or something like that. Then you might have constraints which limit those simulation parameters. Maybe they recognize this is an implausible combination of color. Okay? Alternatively, you can have requirements which, after a simulation run has occurred, observe the results and determine whether or not it's a legitimate result for it. So we can set those up as well. That's more advanced, but for some situations, you want to use this. And there's some underlying statistics which relate to sort of the interpretation of getting this to stop automatically when it's run enough replications. In other words, when it's run enough realizations, what I call realizations, enough runs again and again and again and again with the same set of parameter values that will help sort of limit the number of, say, okay, that's enough. That satisfies the criteria that I've specified here. So you can specify sort of what's the relative level of error that you want to ensure in there. Okay. Okay, so let's just run this to get a bit of a flavor of it, and then unfortunately we'll have to stop. So within this calibration, you right click on it and do run, and what we'll see is some historic data here, and what we're going to see is up at the top attempts to kind of find. So we're going to run this calibration, and we're going to see it's making progress in terms of how closely it's matching these results. And we're going to see down here at the bottom sort of its current best attempt, or its current attempt, shown in blue, and then the best output thus far that it's found. And it's going to be reporting sort of the current attempt it's trying, and then the best it's gotten to. So let's run this. Okay, so you could see the current is there. It's not particularly good. It's trying. It's kind of flailing around. It's trying these different. Okay, this is the best one it's gotten thus far. Okay, it's tried those. Okay, it's looking for a better match. Okay, that's the best one it's gotten thus far. And you'll notice it's using both my cores here. And this is a measure of sort of how good it is thus far in terms of its fits. Okay, and so it's trying different runs. What's happening right now is the red and the yellow, I think, are quite overlapped here. So it's actually gotten a very, very good match, and that's why it's a little bit orange right now. But basically, it's trying to fit this, and over time, it's learning from its experiences, and it does this in a very sophisticated way that kind of takes into account what its best guesses have been thus far, and tries to, if I'm not mistaken, use genetic algorithms, in other words, to try to sort of combine the features of its best guesses thus far to even get better guesses, etc. So this is an attempt to sort of find adequate solutions for here. And you can see it's actually improving quite a bit over time. Its current guess is pretty darn good. So I was wrong that it was overlapped before. Just for some reason it stopped showing it for a little bit. But this is sort of the best guess thus far. It's actually very, 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 very nice. So if any of you are interested in finding out more about this process, just be aware that, number one, it does take into account these replications in the way that I showed. So if you go to calibration here and you go to replication, you'll find that it is using 5 replications per iteration. In other words, 5 times it's for a given vector parameter values. In other words, for beta equals 7, mu equals 0.3, beta equals 0.7, mu equals 0.3, and tau equals 13. It'll be running that 5 specific times before, and kind of reserve judgment until all 5 are done, and then say, okay, this is the level of match to that. So there's a fair bit of variability within that. So if you run this thing, for a while, you'll find it can ultimately match very well. This particular scenario is designed to illustrate the basic mechanism without with minimal complexity. What you'll find is that you could quite easily generalize this to handle matching many outputs at a time, and adjusting more parameters. But bear in mind that if you add more parameters, it's going to take longer, and there may be more combinations that are adequate. Well, there's an informational limit. I don't think the limit is so much imposed by AnyLogic as it is that I'm aware of. I'm not sure if there's any practical limit in AnyLogic.
As far as I know, there's no limit whatsoever in the number of parameters, but the ability to get a useful...
Exactly.
For example...
It's an identifiability
right,
issue.
As far as I understand, the actual minimization, because this actually is the calibration of a specific form of an optimization experiment in AnyLogic, which is why it requires OptQuest. And I believe the optimization is minimizing the chi-squared value between the data set they give you and the data set it has. That it's generating.
Yeah, in this case, it's minimizing the least squares, but yeah.
Well, right. Well, it's a very similar type of idea.
Very similar. Yeah.
So the idea is if you put in multiple data sets, you're going to have to give it some sort of composite minimization objective function.
Exactly.
So
like, so you're gonna have to weigh all the different things and how important these parameters are to see, to get this off.
And this is actually exactly some of the slides that I didn't concentrate on back here, but in this case, and there's actually some fairly grounded theory as to, based on statistical considerations as to how you might weight different criteria, but fundamentally you're going to need to give different weights to different data sets, and indeed sometimes even data points within a data set if there's greater sample size for some of them or what have you.
Now, what you could do though, instead of using calibration, because calibration is using OptQuest, and OptQuest is heuristic, it's not going to search every single collection of parameter values.
It can't.
Right. Well,
it's impossible typically.
So, I mean, the point is, if you had a somewhat limited number of set of parameters you want to test, you could actually create a parameter variation experiment and calculate it as an output metric, the fitness of this, and then you could check every single different combination of those parameters and get an output for them so that you can say, what's my best choice for these parameters? So you can do that as well. I would say use calibration when you can. It's good. I mean, I use the optimization experiment a lot because all of our commercial clients, I hate to say this, but they want to know what to do. They want to turn simulation into a normative and basically prescriptive tool for them, and that basically requires optimization. So, as opposed to an exploratory, very descriptive tool, which is what simulation is by nature. So.
Question, Bill.
I was just thinking, I think the calibration really needs to organize
Right. Right.
that's what classification
Right. Indeed. Yeah, I think certainly there's in parameter variation experiments, there's an art to picking your judiciously picking the sets of parameter values that you end up exploring to understand variability in model results. In calibration, you are you don't have the freedom to just say, I only want to examine extremes or what have you. Instead, you want to be very careful about what parameters you choose and what data you can bring to bear on it and so on. So I appreciate your comments along those lines. So, in terms of what Cheryl was asking, in terms of limits on parameters, the limits are not so much coming from the parameter side as sort of constraints on identifiability, that at some point you just don't have enough data points to distinguish between many good fits, for example. If you have too many parameters, there may be many good fits. Well, if your model structure is off, there may be none. But if there are decent fits, there may be many of them. So, having more data brought to bear is important. And adding parameters to tune leads to a lot more time to undertake it. Adding too many parameters can lead to undetermined, and all constraints are within the fit of the model. Yes?
I have an observation based on the problems that I have had with this calibration. And it is the fact that when I started working on this model, I did not foresee what should I take for calibration.
Yeah.
So when I have the model, now the model does quite a few things, but it's extremely hard to calibrate because the variations are too many. So how one can be more, let's say, astute or intelligent or whatever it is at the beginning when you are developing to get to know what is how should we get there and be able to calibrate. I have a population in this case, so that's the only data I have.
Yeah.
But at the end of the game, it's been not easy, let's say.
Right. Yeah, I mean, I've spent much of my time in the past number of years, in the calibration front, and I will say that one critical consideration, unfortunately now erased, is the whole scoping of the model, particularly between what's exogenous, endogenous, and ignored within a model. You'll find a variety of approaches to the calibration, to the theory of calibration out there. As I noted earlier, I'm kind of increasingly influenced by sort of Bayesian, sort of computational statistics approaches to this sort of issue. But you'll find some people, for example, with a very complex model, as you might be dealing with, I'd want to talk more about your model, they do calibration in sort of a way they call unpeeling the onion. So they calibrate the internals, so the most core parts of the model first, and then successively add pieces in and sort of calibrating sort of additional parameters over time while adding model parameters in. The idea being that you pin down the most important parameters and the parameters least likely to be affected by others, you know, early on, the most critical parameters, and then you add successive components in. I've been fairly lucky in working in fairly data-rich environments where we can actually successfully calibrate against the historic data available, but it's only been as a result of learning from the calibration. So I find I spend a huge amount of time in calibration learning what it's telling me. You gotta learn and you gotta listen to it and pay attention to what it's telling you about problems. Because if you just view it as a routine process, you throw computational horsepower on it and you expect to come out with the answer, I think a lot of the times you're fooling yourself. You gotta figure out what is it that's troubling it and try to learn from that process. And I have a bunch of slides here dealing with calibration process. I don't have time to talk about, but you'll find some discussion by me on my YouTube videos about these. You know, when calibration is bogging down or having trouble, how do you learn from it most effectively? How do you learn the lessons maybe for model structure? How do you learn the lessons for what data is needed? How do you learn the lessons for prioritizing your data collection? How do you learn the lessons for adjusting your prescriptions for parameter ranges? These are not easy issues, but there's a set of sort of fairly good heuristics you can use to kind of challenge yourself and learn what it's telling you. Because if it's having trouble, it's often something you should really put time and invest time in to understand what's going on here, and that will let you go forward with greater confidence about different paths. So it's a somewhat abstract answer. I need to talk about your particular model, but suffice it to say, this is not so much, from my perspective, this is not so much a computational process of just go get it done. Run it on massive number of cores and come out with numbers or something like that. The fundamental issues here is learning and insight. And if you can leverage that effectively, you'll be much better off in your modeling because it will help you refine your model, and it will help you sort of arrive at greater confidence in model results. Scott, did you?
Well, I mean, I ran into this. This was actually one of the first things I had to deal with. It was actually with the very, very close cousin of calibration being validation, because, for example, in discrete event simulation, which is my background, you don't do a lot of calibration. In fact, I've never heard the term. But you do have to do validation, which is trying to match to the real world, so it's a very similar idea. In my first project, I was just actually monitoring a Walmart checkout, okay? And my model would not validate, and the model was simple, and well, it's before I worked for AnyLogic, and I did not know why. It turned out that what I thought was my arrival pattern was actually two separate data distributions. And so I had to go back and collect more data and separate the people who were coming in from the grocery side of Walmart, who were coming in from the rest of the store at Walmart, actually arrived in a different pattern. And so I had to collect that data differently. And as soon as I did that, the model validated. Similarly, with my first consulting project, I was given data, I was given a process. I modeled the process, and I knew something was wrong because it was basically a business process and had a security checkpoint at the beginning, and it was telling me at the end of the day, 800 people are in a 10 by 10 room. way to go through security.
That sounds realistic to me.
Well, okay. But the thing is that, and so.
I think you mean 10 by 10 feet.
Did I say something else?
Well, you're from south of the border, young man. We use metric up here. So.
Square meters having 800 people in there
Yeah,
sounds
no,
a bit
it would be-
low.
it would be too much.
But anyway, but what happened is that this was really a cool thing for me, because I had this model and I was pretty sure that the model logic was correct. But the model output was useless. And I did not know if it was the data they gave me or this. And so we went to the client site and I was supposed to show them the completed model. And I told them flat out, this model is not valid. First of all, half of the room didn't know what it meant. The other half apparently didn't care. But, so we actually got the actual location that I was modeling on the phone, and there's like, yeah, about this number, is this about right? And every single time they told me no. In short, every single number that I was given was wrong. They told me it took a minute to go through security. No, it was about more like 3 seconds. That's going to change your output, right? So we changed all the numbers, and my model immediately gave out the correct answers. Once you just change all the parameter values. It was really cool, but it's really a good point that if your model doesn't calibrate, it might be because you're giving it the wrong data. Your data is not, I won't say corrupt, but it's not the correct distribution. You know, for example, one of the training classes I was given, the person knew that they weren't collecting the right data because they were collecting total number. No, they were collecting number of new cases from a system dynamics model for calibration, but they needed the number of total cases, and that's what their data was. They had to ask me real quick, and it's a very simple thing, how would I actually calculate the total number of cases, not just the number of new cases that are happening in here. So this is the sort of, you know, questions, at least practical kind of questions I've had to deal with when dealing with calibration and validation.
Those are great war stories, and they actually presciently sort of mirror some of my own experiences. And again, this is your opportunity to learn. It's not just a check thing to check off the list to get beyond so you can do the real work with your model. This is often where your model gives real insight, and it can be insight to your mental model as much as it is to your actually design of your physical model. So there have been several cases where, like Scott, things just didn't jibe. We tried lots of things, it didn't line up, and we were doubting our model in a big way. And we noted this to clients that we were having trouble with these things. And in both cases, I remember off the top of my head, one case, what had happened is the data was from a source where if you went back and looked at it, the definition had changed in 1 year in the middle of it. So we had several years where you had one definition of what was being collected, and then later years it was a total different definition. And so it didn't jibe for good reason. And you know, in another case we had, it was with our TB control program, we were matching things beautifully except for a certain year range. And in those year ranges there was a distressingly large number of TB cases. And we went to our TB control program, we said, you know, it's doing a pretty good job, except for these years, we're really concerned we're missing an important cause for an outbreak or something. And they said, oh, just forget about those cases. So during those years, there was a changed definition of incipient TB that ended up treating a lot of cases that were merely incipient as cases of full-blown active TB. And so fundamentally, it was, again, a data definition. We'd never found that, except the model told us it didn't make sense. And once we knew that, it helped our appreciation for what was going on historically. What was going on historically was actually quite well captured by the model, and it was telling us things we hadn't anticipated when we built it. So calibration is one of the big areas where you can learn from your model. Just give it the patience, give it the respect it needs, and try to find ways, and I've provided a bunch of suggestions in my slides, and on the YouTube videos, we're trying to learn from it, trying to you know, listen in and figure out what's giving it trouble, because that will be to your benefit. Okay. Yes.
When I want to calibrate two
data, historical
Yeah.
data,
Sure.
say, I don't know, unemployment numbers
Sure.
and wages.
Sure.
Mhm.
Yeah.
And it's not, it depends on units now, and there's like some weighting.
Well, yeah, and so that's what's discussed in some of the slides I wasn't able to talk about. You want a measure that's dimensionless, ideally, so that you can add things together in a way that won't cause dimensional problems. So just to give an example, you don't want to add a discrepancy in dollars to a discrepancy in persons, because it doesn't make sense. And so often what will be done there is to take a fractional discrepancy, so you're off by 10% in this and 1% in that. But there's other ways to deal with it too. You're going to need very critically weighting factors that sort of give you how important, among other things, that matches for the purpose of the model, but also sometimes it's considerations of the statistical reliability of certain of those data. Because some of the data may be with a lot fewer sample points, and it has much greater variability. If you look at incidence data for something like TB in our province, and jumping all around month to month and so on, and you look at something like, well, even for TB, screening data for community screening or for screening of kids on a systematic basis, and you'll find greater stability in other types of data like population size, which you may also want to match. There's much greater reliability statistically. And so those weights should take those things into account. I'd be glad to take this up with you if you're interested in talking about some of the approaches we've used. But there's some formal statistical theory about how do you weight estimates according to their statistical reliability that could be used here. Okay.
Just my question is any way, maybe it's, is any way automatically troubleshoot if your model does not calibrate, it's not finding a good fit? So whether it is in some
Yeah.
problem in the logic of the model,
Right.
or it's not just finding the
Yeah.
right combination of parameters, is there any way that you can, other than trial and error, for you to identify, to not spending a lot of time trying to move in every direction, finding the right numbers, but then the problem is
Right. Right.
is there any way to troubleshoot that?
Yeah, there are ways. For me, it's very much a manual process now. That process of sleuthing what's bothering it. We do have some tools that we've created that aid in the calibration problem diagnosis phase, but they're all pretty simplistic tools. So that they don't really get to the essence of the issue of kind of interpretation. I mean, often what I do is I sleuth around. I say, so often I'm matching like two time series or 3 time series, and or maybe it's it's matching well for these points in the time series, but not for those, or something like that. And so I'll try to sort of poke around and figure out, okay, why is it can either match these or those? What's the fundamental tension here? Why can't it match both? And that has to do with model structure often. I didn't realize that, but if it really, there's no way it could grow that quickly without this being high, and that would mean it wouldn't match those. So often it is sort of a trial and error process, but it's not shooting in the dark. It's not scattershot. It's like a systematic sleuthing that goes on, and these are things that I've sought to teach my students who are involved in calibration before, sort of how to go about investigating these things. So I think if you have someone who's done it before, it's not like just total guesswork or shot in the dark or just sheer luck. They're able to get beyond this. They're able to get beyond it because they have a systematic approach for problem solving. Is really what it comes down to. And I have some rules of thumb there, but really we're not talking about something that's just incredibly difficult. It just involves patience, being systematic, being very careful, meticulous, and observant, and thoughtful. about what's going on, and there is some trial and error, trying things, so why didn't that combination work? Let's give it a try, let's see how that affects, oh yeah, that doesn't work because this other thing is off, okay, well, why is that? And occasionally you find a bug in your model. Often you find more that the model structure has something that just doesn't jive. Like, I remember in one case, it just wasn't matching because we hadn't distinguished at that point between infectious and non-infectious TB cases. And as you know, in Canada, a lot of effort is put into finding active TB cases when they're not yet infectious, when they're heading off that infectiousness. And this is quite important for capturing some of the data. And so once we made that distinction, things lined up just much better. So it helps us really arrive at a much more reliable model. Okay? But I'm glad to take these things up with people. But I've taken too much of your time. Today is our chance to work further on projects. I will be giving a Java tutorial as well. For those who are interested, we talked about the subclassing issue, this issue of capturing commonality, among other things, and I'll also be talking about probably a little bit about creating functions, which are a good aspect of software engineering hygiene that I haven't been able to really do justice to in this boot camp. I will be, as normal, recording those, so if you can't make it, I would encourage people to think about working on the projects and advancing the projects, but I will have those things online so that you can refer to those. Okay? Okay, great. Thanks very much. About 5 minutes. Yeah. So we're going to start with that. We're going to have more time after that for projects, and then we're going to have some project reports, saying at least where you are right now. Okay, so how are things going for projects who feel moved to do that? Okay. Yeah.
We're leaving in about half an hour.
Oh, really?
So yeah.
Okay.
It's really just grabbed my attention a great deal. So I just wonder whether I could make a touch base with you by email.
Delighted.
So I work at the Verted TB control program.
Really?
So with Dr. Long.
Yes. I didn't know that.
Well, because I just joined a few months ago.
Okay.
I just fairly new there, so I came there just in the end of May. So but I have my main interest in these clinical disease, infectious disease epidemiology, and I'm looking at maybe setting up some programs. And I'm looking at this as a possibility. Well, before coming here, I knew